Welcome to this episode of Georgia Highlands College Chemistry Podcast. Recently, we have discussed the periodic table and how it was discovered and how it was set up. The guiding principle behind how the periodic table was set up is the periodic law. The modern form of the periodic law states that the properties of the elements are periodic or repeating functions of their atomic numbers. Therefore, the periodic table is laid out to reflect these periodic trends. In this podcast, we will talk about some of these trends and why they exist. These trends can be explained using two main concepts. The first concept is electron shielding. Electron shielding increases from top to bottom in a group. The second trend is nuclear attraction or effective nuclear charge, abbreviated as ZEFF. Effective nuclear charge increases as we go from left to right in the periodic table. By understanding these two trends, we will be able to understand all of the periodic trends. We're going to first look at electron shielding, and we're going to look at the lithium atom in our discussion of electron shielding. The lithium atom is in period 2, so N equals 2. Lithium has an atomic number of 3, so lithium has 3 protons in its nucleus and 3 electrons. The first 2 electrons in lithium atom go into N level 1. These are known as the core electrons. The outermost electron goes into the outer shell and is known as the valence electron. So lithium has 1 valence electron and 2 core electrons. These core electrons do not feel the same force of attraction from the nucleus as does the valence electrons. The core electrons are much closer to the nucleus and therefore feel a larger charge. The outermost electron is shielded by these innermost electrons. The innermost electrons also repel slightly these outermost electrons, decreasing the effective nuclear charge. So the way that we can calculate the effective nuclear charge is using the atomic number, the number of protons, minus the number of electrons on core levels. So the effective nuclear charge for lithium is 3 minus 2 or plus 1. When we go down to N equals 4 in the periodic table, we're going to look at potassium. Potassium has an atomic number of 19, so it has 19 protons and 19 electrons. It has 4 N levels. 2 electrons go into N equal 1 for potassium, 8 in N equal 2, 8 in N equal to 3, and 1 in N equal 4. So potassium has 18 core electrons and 1 valence electron. Again, these core electrons, these shield the valence electrons from the full force of the nucleus. So we can calculate the effective nuclear charge here. The effective nuclear charge is 19 protons minus 18 core electrons to give us an effective nuclear charge of 1. So both lithium and potassium have an effective nuclear charge of 1. Now we're going to go to increased nuclear attraction or effective nuclear shielding. Again, we have looked at the lithium atom, and it has effective nuclear charge of plus 1. If we move further to the right in the periodic table on period 2, we will go to the fluorine atom. Fluorine has an atomic number of 9, so it has 9 protons and 9 electrons. We have 2 electrons on completely filled inner levels, the core electrons, and we have 7 electrons in the valence shell. So these 7 valence electrons do not feel the complete force of the nucleus. They are shielded by the core electrons. The effective nuclear charge for fluorine are 9 protons minus 2 electrons on the core completely filled inner shells. So 9 minus 2 is plus 7. The effective nuclear charge of fluorine is greater than it is for lithium. So you can see as we move from left to right in the periodic table, the effective nuclear charge increases. Now, how can we apply this to trends in atomic radii? First, we're going to consider going down a group. We're going to use our lithium and potassium example. Both lithium and potassium have a +1 effective nuclear charge. Therefore, what must control the size of the atom are the end level, the primary end level. Potassium has more energy levels, is further down in the periodic table than lithium, so therefore it is a larger atom. So as you go from top to bottom in a group, the atomic radii increase. Now, how does this compare as we move from left to right in the periodic table for atomic radii? We're going back to our lithium and our fluorine atom. Lithium had a +1 nuclear charge and fluorine a +7 nuclear charge. Each one valence electron in the lithium atom fills a +1 charge. Likewise, each single valence electron in the fluorine atom fills a +7 nuclear charge. Therefore, a stronger force of attraction is felt by the valence electrons in fluorine than they are in lithium. This stronger force of attraction causes the fluorine atom to be smaller than the lithium atom. So we can see that an increased effective nuclear charge, as we go from left to right in the periodic table, causes the atomic radii to decrease as we go from left to right in the periodic table. So in summary, how do periodic trends affect atomic radii? So electron shielding increases as we go from top to bottom in the periodic table, and therefore the atomic radii increases as we go from top to bottom in the periodic table. Likewise, the nuclear attraction, or the effective nuclear attraction, increases from left to right in the periodic table. And therefore, the atomic radii, as we go from right to left in the periodic table, increases. So we can see that an understanding of the two concepts of effective nuclear charge and electron shielding can be used to explain periodic trends. Atomic radii is the only one that we're going to discuss in this podcast, but the same reasoning can be applied to the other trends that we're going to see in our chapter dealing with periodic trends. Thank you for listening to this episode of Georgia Highlands College Chemistry Podcast. We hope this episode has helped spark some interest and excitement in chemistry. We look forward to sharing more chemistry podcasts with you in the future.